Let's again take a look at the details of the long path from a YouTube server to your iPhone. Okay. Let's start from your end. Okay. So usually there is, well, here's your cell phone, okay, to the tower. Okay. Now this tower could be a Wi-Fi or it could be a cellular one. Okay. Let's say it's a cellular one. The cellular one goes into some kind of box. It's a switching center, controls a lot of the mobile base stations. From there on, it goes into something called the core network. It's the core cellular network. Inside, there are many, many hops and boxes. Some are called S gateway, some are called P gateway, and so on, depending on which generation you're talking about. And each of them may be further connected to databases and different softwares and servers. Okay, and then this will then go into the rest of the internet. There's a little terminology issue here. Some people refer to this part as the internet, whereas I guess strictly speaking this whole thing is the internet, because the internet is really defined as a network of networks. So it goes into further hops. There will be routers of various kinds, okay, and part of this may belong to the same company as the company providing the cellular, for example, AT&T, okay, and part of that can belong to a different one, for example, Sprint, okay. And then it will go into another cloud, which is the Google cloud. And Google is a very special case. It's got a huge network itself, okay. And then once it gets into the Google cloud, it may be directed into a particular data center. Okay. Within data center, there's actually a data center network, and then we'll find a server. And this server controls the video. Okay. It may also go to another server that controls the control messages. For example, is it pause, is it playback? What kind of playback format are you using? Okay. And the actual content of the video itself, all those bytes are stored here in the server. So as you can see, this can cross multiple companies, right? And it can cross, 10, 15, 20 hops. Just like modularization is implemented by layering, the physical span of the internet is a large object, is done through some kind of distributed hierarchy. For example, the ISPs, the Internet Service Providers, form a hierarchy spatially. These blue ovals represents what's called Tier 1 ISPs. These are big companies offering network services. For example, NTT or BT or AT&T and so on. Okay. And they usually form a peering relationship. Okay. A very dense, one could view it as a full mesh peering relationship that says that they can directly talk to each other. Okay. Without these peering relationships, people in Britain may not be able to talk to people in America. And that's not a global internet. So the fact of a global internet is because this network is supported by a backbone of tier 1 ISPs interfacing with each other through peering links. These are physical objects. Okay, they're actual undersea fibers connecting different points. But they're also business relationships. And they often look at the traffic and say, is too much AT&T going to BT or too much BT going to AT&T traffic? If there's too much asymmetry, then the party receiving more traffic may start requesting a payment to say, look, I'm helping a lot more of your customer than you're helping my customers to have a global connectivity, so I'm going to charge you for the differential. That's one of the reasons why they want to look at the balance of the traffic flow through routing to maintain a stable connection, peering business arrangement. Then there are many tier 2 ISPs, they're still pretty big. Okay, there are national or regional ones. They form actually links among themselves too. Okay, peering links. Sometimes it's very hard to measure these. Thus, the AS autonomous system graph is actually hard to construct. Now we call these tier 1 or tier 2 or tier 3 ISPs, each of them forming an autonomous system. AS is basically something that's under your control as a company, including the routers and the links. Eventually it goes into what's called a stub ISP. For example, a campus or corporation ISP that does not really offer any transit services. Okay. Then, of course, there are customers, real end users like you and me connected to the stub network or tier 2 or directly to tier 1 ISPs, depending whether they have a residential consumer business or not. We also call the collection of devices controlled by each autonomous system a domain. So when we talk about routing soon, we have to talk about routing within the same domain or across different domains. There's another spatial hierarchy called the overlay network. For example, peer-to-peer networks such as BitTorrent, which we'll talk about in lecture 16, or content distribution network that we'll briefly mention advanced material part of lecture 17, like Akamai. They all can be viewed as overlays on the internet. For example, the actual internet may look like this. And the overlay may say, you know what, I don't care about these nodes, I only care about these two nodes, A and B. Okay, so as far as A and B is concerned, it's like there are two paths connecting them. Well, one path and another path. So my overlay topology is like this, even though the underlay is like this. So the overlay connection could be a logical concept. Okay, if you really dig in, it's actually many physical links underneath it. Now, P2P CDNs are actually overlays built on top of the internet, which is in turn can be viewed as an overlay built on top of the old PSTN telephone networks, together with other networks. Now, the idea of overlay is powerful. It says that what really counts is economical, scalable connectivity establishment. If you can provide me with easy, cheap, and scalable connectivity, I can take care of other things by building an overlay network with my own policies. Okay, so the needs and application and services arising in the future, the unforeseeable future needs, let's just leave that to the overlay. Under-specify the protocol so there's enough flexibility to build the overlay and give me really cheap, scalable connectivity. That is one of the secrets behind the success of the internet. All right, so now I've touched upon all three most powerful ideas behind the internet design. Okay, packet switching, layering for evolvability, and spatial hierarchy. That was a long introduction. Okay, if you are reading the textbook, you see this is a short answer that's actually longer than the long answers section of the chapter. But it's also very exciting. It's easy for me to talk about these things, okay, as if I'm talking about the cereal I just had as breakfast. But actually, it wasn't that trivial at all to be able to come up with these wonderful ideas and execute them right in the last 40 plus years. That's how we got the internet we're using today. And that's how this course is being distributed to you through YouTube or other platforms today. All right, now back to our subject matter. How does traffic go through the internet? Well, equipped with these understanding, we can now talk about IP routing in the network layer. This actually is a huge subject. You can write multiple books just on routing, on IP. For example, there's inter-domain and intra-domain routing. Okay, routing across business entities is very different from routing within. There's unicast, which we're focusing, versus multicast, which we're leaving to P2P based routing in the application layer in future lecture. So we are going to focus mostly on unicast routing and routing within a domain. Although in the advanced material part, we'll briefly talk about interdomain, BGP. Now you can talk about routing over a single path. Okay, find me a path versus leverage all multiple paths possible. We will focus mostly on single path routing. You can look at best effort routing, which is our focus, or add other features to ensure quality of service to some extent, for example, accelerated delivery. There are also other kinds of related subjects, for example, switching in layer 2 in the Homer problem. Routing in a wireless network and optical networks takes different forms, but we won't have time for those. Now, when we talk about routing, there are actually three things we have to talk about. One is addressing, then routing decision, then actual forwarding action. Let's start with addressing. This is basically giving a label, because without label, we can't possibly know how to route. In network layer, there's something called IP address. It's usually written in this kind of format. Okay, it's a 32-bit, but you usually write it in decimal format in blocks of 8 bits. For example, 127.12.5.88. Actually, I have no idea what machine corresponds to that IP address. Okay, if you think about a transportation network, it often offers interesting and intuitive analogies to the internet. We'll be using a few of them in the coming lectures. So here's one. Think about the mail system in your country. Okay? In most countries, the mail system has the following feature, right? You give a label to an address. Okay, this house has a certain label. It's a street address, or maybe a PO box number. Now, whoever lives here actually has some personal identification. It's an ID. But you don't mix up the personal ID with the label. However, for whatever historical reasons, in the internet, actually we use IP address both as a labeling method for routing and also as an ID. And this creates a lot of problems. For example, how do you handle mobility then? Well, it wasn't part of the story back in the 60s and 70s, but now it is. Perhaps the dominant part of the story is on cellular mobile traffic. Then the IDs and the label should really decouple. All right, back to the original design. They also have something called a prefix. For example, 127.12.5/. Basically, this is like a zip code to say that there are 8 more bits, but I'm not specifying them because they all belong to similar kind of companies or maybe similar locations. So this is like the zip code. Okay, I give you a zip code to help you quickly zoom in to the right part of the country that you can deliver the mail to. Now, you have heard of the transition we're going through from IPv4 to IPv6. This is version 4, this is version 6. Okay. Again, standardization, historical accidents. That's why we're not talking about v3 to v5. Now, we've been using IP version 4 for a long, long time, 32 bits. And back then, 40 years ago, people thought that 32 bits was a lot. Okay? 2 to the 32 is a big number. Are you sure we're going to need that much? There were a lot of people thinking that maybe we only need 8 bits. Okay? Because, 2 to the 8 is about as many machines we'll ever need to connect. And what is 2 to the 8th? That's a very, very small number. Okay, it's what, 256? Right. So they thought that maybe, there'd be like a couple of hundred of mainframe computers around the world that we need to connect. And then that's all we need. Well, fortunately, they took a much bigger number, 32, too. So 2 to the 32 is a lot more, but we run out of the addresses. Okay, so now they say, well, let's really make it this big now. Instead of talking about 32 bits address, let's make it 128. Okay, so now it's 2 to the 1 28. That, we hope, is going to give us enough time. Should last quite a while. But then again, the way that, toasters and everything got IP address, and your personal device may collectively have 20 different IP addresses already. So, and when we have machines have multiple IP addresses, we may later come to a day when that is not enough. In the old days, these IP addresses, IPv4, were allocated in blocks. So if you are big companies or big vendor, for example, if you're IBM or if you are AT&T, then your customers or devices are given a big block. For example, block 127. Okay, so 2 to the 24, because there are 24 unspecified bits. That many addresses is given to you. Well, it turns out that some of these addresses are not even used, but it's already allocated. So later people switch to so-called classless interdomain routing. Okay, you don't give away blocks of IP addresses, 2 to 24 to class, the top class, 2 to the 16 to the next class, 2 to the 8 to the next class. Even then, that was not enough. We have to switch to IPv6. A little bit more on the IP addresses. Okay, there are actually quite a few things involved in managing these addresses. You're going to see in the next few lectures a lot of these acronyms like DHCP, NAT, NAT, and ARP. These are protocols sometimes implemented in boxes, hardware. You will see so many more of these acronyms, even though we're trying to reduce the number of acronyms, but we just can't help with about 25 of them. Okay. You can have a whole book written with nothing but acronyms. There's at least, a few tens of thousands of acronyms, if not millions of acronyms invented by engineers. It's a little funny, but these are very famous ones. Okay, one is so-called Dynamic Host Configuration Protocols, DHCP. It's a mouthful, but what it does is basically it's a rental service of IP addresses. Okay. For example, at your home, okay, depending on your country and service provider, often what you have is that your laptop here, okay, does not have a fixed static IP address. It has a dynamic IP address assigned to it by a DHCP server. Anytime you get connected to your Wi-Fi gateway, it calls upon a DHCP server to say, all right, in the pool of IP addresses that Comcast can use in the US, give me one that's not currently used, and I'll give it to this device. So your actual IP address visible by the external world is a dynamically allocated one. So you may say, but I want a static IP address. Well, then you have to, for example, in a hotel, pay for more in order to have a static IP address. Then there's something called network address translation, because sometimes in a company there's a firewall. Okay, your address inside the firewall in the corporate network is different from your address visible by the external world. Okay, so there's something called NAT. And then there's something called ARP, Address Resolution Protocol, which is the mirror image of DHCP. Instead of a machine says, well, here's me, I have a MAC address which is etched on my memory. Okay, you can often just look up the MAC address. This is there the moment the device got shipped out of the door. Okay, so I tell you who I am as a machine, you give me an IP address that's visible for routing purposes. That was DHCP. Now ARP is the other way around. It says that, well, if you tell me the IP address you tried to look for, then I'll return to you the corresponding MAC address. So there's a lot going on in address management. Now finally to step number 2, routing. Once you have the address and label, then you can think about routing. One type of routing is metric based, like shortest path routing that we will encounter in the next module of the video. There are also other routing methods like policy based. It says that you might be a better path, I don't like you, so that's my policy. I'm not joking. This is real. Okay. In advanced material, we will talk about BGP's policy and filtering that can change the decision made by metric-based routing. And in metric-based routing, there are two main families, each with multiple variants. One is called distance vector. One is called linked state. We will focus on distance vector in 2 more modules in the video, and then in advanced material talk about linked state. So here are some famous ones. For example, the most famous distance vector routing is RIP. Okay, it was used in the original ARPANET. It's used in part of the interdomain routing BGP. The most famous linked state routing is called OSPF, Open Shortest Path First, OSPF. We'll talk about this in advanced material, together with the most famous policy-based interdomain, okay, routing across autonomous systems, across business units, companies, called Border Gateway Protocol, BGP. So RIP and OSPF is routing within intra-domain. BGP routes across domains. What we will be focusing on is really just RIP before advanced material. So finally, the last step, forwarding. Now that you have a routing decision made, okay, you actually need the physical action of forwarding a packet from one point to another. Okay, so think of, again, the mail system. Right? You got address, you got a routes. Usually the routes are predetermined. It says that going from Princeton, New Jersey, USA to some address in Mumbai, India, well, you're going to follow a certain route. For example, go to New York first, and then New York go to Frankfurt, Frankfurt goes to Mumbai, for example. Okay? That's routing. Now, in the mail office, you actually have to do the real forwarding. And usually the forwarding goes like this. There's a guy standing here and looking at this mail with a stamp and the address. And I say, all right, I look at the address, and then I have a lookup table that says anything that goes to India first goes to New York. Notice anything that goes to London may also goes to New York. So New York is my next hop. So my job is to pick the next hop and forward it there. Okay? So many different destinations may share the same hop. And notice I only look at the destination. Suppose I'm in New York now, okay? And I look at this mail going to Mumbai. I say, well, next station is Frankfurt. It goes to Frankfurt. I do not care where this has traversed, whether it has gone through New York or San Francisco. I don't care. I just look at the destination, and then there's a lookup table to tell me the next hop. That is exactly the philosophy adopted by the majority of the internet routing protocol. When they do the actual forwarding in a router that implements the routing policy, they do the destination-based hop-by-hop forwarding. In contrast to source-based or source and destination together. Of course, you need to base on, in part at least, on destination, but also based on the source. And maybe the whole history of where you have been. So that's the majority. But there are also other kind of forwarding mechanism. For example, multi-protocol labeling system, MPLS. Okay, so this is a different kind of forwarding. Okay. Actually, I said multi-protocol label switching should be. Too many protocols. Okay, MPLS. This is a layer 2 technology that basically provides a label management that says, when a mail comes in, I'm going to stick a label on it, and then the next one will stick another label on it. So you're going to actually look at the label, and the label will basically pin down a specific path for this mail or packet. And the forwarding depends on the label, capturing actually the history of the spatial memory. Okay? It's not just destination-based and hop-by-hop decision anymore. But this, of course, as you can see, tends to be harder to manage. It has more overhead and complexity in managing it and debugging it. So what happens in a router, okay, is the following. There are many ports, okay, and there is a switching fabric that can have many different physical implementation. That's beyond the scope of our course. When a packet arrives at a port, we're going to label that the input port for that packet. And now your job is to have a lookup table and find in this forwarding table, what does it say I should do now? Okay, it basically maps a destination IP address or blocks of IP addresses to a particular output port. Okay, and I say, all right, all the destination IP address in this group basically will go to this output port or this output port. Then the switch fabric will push that packet over here, usually by reading and writing into and out of memory. Now, there might be congestion. For example, this lookup table, which could be in the central control plane, or it could be duplicated on each of these so-called line cards. Okay, these are basically the degrees of these routers for each connection. Okay. You can have this lookup table either centrally or locally. Now, you may have congestion if either because the arrival of the packets is too fast for either the switch fabric to check with the forwarding table, or for the outgoing ports to process it. Okay, arrives too fast, it will be congestion. There could also be congestion if there's a packet waiting to go to this port, but this port is busy, it's very congested. But all the other packets waiting behind it is actually targeted for different ports. It doesn't matter unless you implement some smarter policies of forwarding. Otherwise, first come, first serve, you guys got to wait, even though your destination ports actually are free at this moment. So congestion can occur for two different reasons. Next lecture, we'll look at congestion due to too fast incoming packets. Now, in the next module, we will go into a specific routing. You have seen there are so many dimensions and so many variants of routing. We will now zoom into one single specific case for the rest of this lecture before advanced material. And we'll start out by talking about a mathematical optimization problem. It's actually a linear programming problem on a graph called the shortest path problem.